Guys, welcome to Anatomy Physiology lesson 1010 on the spread of action potential. I've got a few notes already written because I just have not been able to record this video. I think I've messed it up about 4 times, so I didn't want to go reprint my sheet. But what we're doing is we're looking at an axon. And at the last time we looked at what happened at a single point. And then this time I've got a whole axon. And what I did was I tried to draw this as part of a nerve cell, and it didn't go very well. So if this was one side of my axon, this is inside the axon, outside the axon. The other side of the axon would be here. I'd have my axon hillock. These were supposed to represent dendrites coming up, and my cell body, and my nucleus, but you know how I am with drawing. I'm usually a little bit less than. Down here, then we would have the axon terminating in those axon terminals and the synaptic knobs. So, see if I can draw this. So that's my whole neuron, and we're looking at the whole length of the axon now. And one of the things we need to note is that this is an axon that does not have a myelin sheath. It's a non-myelinated axon. Can we have that? Absolutely. A lot of neurons don't have myelin. And so when this nerve pulse gets conducted, it has to get conducted along every spot along the whole axon. So we call that continuous conduction. Continuous conduction. So we conduct at every point. Now, I am going to draw in, if you remember correctly, the light colored purple in the last video was our sodium ion channel. So we're going to make, this is going to be our Na+1 ion channel. And this is a voltage gated. So this isn't the sodium potassium pump. This isn't the sodium potassium pump. This is a passive. And I'm going to, instead of going with dark purple, I'm going to make blue potassium channels. So that we can really see the difference on this. So what's going on when I start is that I have here a closed sodium channel. And I'm going to use black lines to represent that this is closed. Just like we saw in the last video, and I'll kind of outline here. So this is one sodium, voltage gated sodium ion channel. It looks like 2, but this is the gate. So here's the gate. If you look at the last video, I kind of tried to draw it like it was in the last video. So this is at rest. So at the start, the membrane is completely polarized and we're at rest here. So what's going to be the voltage on the inside of the axon? Well, hopefully you know by now that's going to be -70 millivolts. My gate's closed and we have a signal that comes in. So we get a signal comes in. And what's the first thing that happens? When that signal comes in, hopefully you remember that it's going to open up this, and I'm going to change this to dark purple. It's just not showing up very well. That's what I mean. I've just been having some issues on this video. So here's the channel. So now the signal in causes the gate to open. So we've got an open gate, and you'll see here comes the sodium. So the sodium's going to come pouring in. And our caption says, when an action potential is initiated, a region of the membrane depolarizes. So what we have going on here is depolarization. And the adjacent region becomes depolarized. So that actually is what we're seeing down here. All right, so far, everything's what we studied in the last video. So we're at rest, -70 millivolts. A signal comes in, it opens up that sodium gate, voltage gated sodium ion channel. And we flip, and you'll notice down here now we have the positive, there's that positive 30. So we flip to the positive 30. So here's what's going to happen. This region of positive 30 is going to trigger the next region to open its sodium gated ion channels. So here was channel 1. And here is the second. And this is by region, so it's a whole region. We have another one over here. It's closed. So when the first region depolarizes, what this means, the adjacent regions become depolarized. It means when one region depolarizes, it triggers the next region. So now I'm positive 30 here, I'm positive 30 here. I'm still negative 70 over here though, because what will happen next is, so we'll see this region is going to trigger the next region. So down here, let's just add in a few more that are closed. So open, open, close, close, close. Now this one's going to be open. This one's closed. This one's closed. So when this one opens, it triggers the next one. This is going to trigger the next one. This is going to trigger the next one. And it spreads down the axon. So this spreads down the axon. Whoops. Just realized I was off screen. Okay, I am not going to stop this and re-record, so I apologize. You can go ahead and pause the video and catch up your coloring. Okay, so let me say that again. We had, when this region depolarizes, it triggers this one triggered this one, this one's going to trigger this one, so on and so forth. And we have a spread. In fact, let me just spread this or move this down so I've got this for the rest of my, holy moly. Okay. So we have the depolarization spreading. Well, what's going on here? You'll notice the potassium is flowing out. This is the repolarization. So after we hang around at that negative, positive 30 voltage for a while, that's going to cause these potassium channels to open. And I get my potassium flowing out. So now I've started, this is the beginning of repolarization. When the membrane begins to repolarize, this is going to trigger, remember, blue are my potassium channels. This is going to trigger the next potassium channel. So here I have this one is going to trigger this one. And you'll notice that down here, my, let's put in my proteins. This one's closed, this one's open. So I went from the first to the second to the third to the third, the fourth. This one's still closed. So this is my spreading depolarization. And this is all going to be at my positive 30. This one, I have the flow potassium out. So this is going to be my undershoot. There's so much that has flown out that I went to -90. But back here at the beginning, this guy's closed now. And the sodium potassium pump, which isn't pictured, has kicked in. And this is going to be at -70. So we go back to the beginning for a resting potential. And it's through this process of one region triggering the next, triggering the next, triggering the next, both in depolarization and repolarization, that causes it to spread. So if let me put a purple dot here on this finger to represent depolarization. And let me put a blue dot on my other finger. So if we look back up here, what's going to happen is the depolarization is going to start, it's going to spread down, and then a ways behind it, remember blue's repolarization, it's going to also start and spread. And we'll just continue down, we'll get to the end here. And that is the end of one action potential. And it's through that spreading. And at each of these spots, what we learned in the last video was when we learned depolarization and repolarization at a spot, it's the same thing, only it's happening in waves. All right, I apologize. Maybe someday I'll go back and I'll just re-record this whole thing. If you get to this and it's just a little too tough to understand, let me know and I will re-record it. But the other thing we have to talk about is what happens if an axon has myelin. So let me grab that sheet. All right, so my cell body would be back here. This is my cell body. And my axon terminal will be down here. So I'm going this direction. And now I have Schwann cells. So this is in the peripheral nervous system. Because I have Schwann cells, remember in the brain, we have oligodendrocytes. And the yellow is my axon. So this is my action potential at a point. I'm usually positive on the outside and negative on the inside, but I've started an action potential. So I flipped my charge. I have my +30 here. Here it's -70, here it's -70. What you'll see is in the next phase, I went from here to here. So my charge flip skips this entire length of axon. And we jump at the signal. So in this case, the signal, you can think of it as jumping. The signal jumps from node to node. If this was unmyelinated and this was myelinated, look at the speed. So I have to go continuous here. This one's doing the jump. It was twice as fast. And in fact, actually conducting on a myelinated fiber is much, much faster, not just, twice as fast, but hundreds of times faster. Conduction is called saltatory conduction. And again, it takes place from node to node to node, and it allows us to bypass this whole area in a sense, bypassing, oversimplifying a bit, the axon that's covered up by the Schwann cell. All right, so what are our takeaways? When we're conducting down the whole length of an axon, depolarization starts at one point and it triggers depolarization in the next region, in the next region. We come down here to the last one. So what we have is this area of this front edge of depolarization where this membrane protein is open, is going to trigger this one to open until we get to the end of the neuron. And a ways behind that, what we have is spreading repolarization. So this region, this repolarized, this potassium channel that opened to allow repolarization triggered the next potassium channel, so on and so forth. And then they close behind and reset the membrane. All right, that is it for conduction down the axon. Thanks for watching. That's all for now.